This is going to be a talk of a different flavor. I'm going to completely, you can relax. It's a good talk for after lunch because it's highly non-technical and you won't really see a single equation that matters. That'll make it easier for a digestion talk. What I want to talk about is tools, computational tools. Computational tools for the kind of work that I suspect many of us in this audience do. Most of us actually probably write code, but we are not software developers in the traditional sense that a team like, say, the people who develop Microsoft Visual Studio, who develop tools for software engineers, think of. We are a different breed of people for whom code, data, and the results that come out of it are completely intermixed in an iterative process where we don't have a well-defined, clearly specified goal of a product that we're going to build in advance. And instead, we tend to iterate with algorithms, with ideas on data that we have. We may be writing custom code that only applies to a specific data set, or at least to a few data sets of a given kind. We may be doing purely exploratory work that may or may not evolve into production code, and production may mean anything from actually shipping a library that third parties will use to simply running it in-house on large systems. Our goal is to answer questions, whether it's publishing a paper in a class of algorithms or understanding something about your click rate, if that's what I know many of you guys do here. The point is we are not in the business of actually picking a specific programming language or being wedded to a specific technology. The end goal are the scientific, algorithmic, and data questions that we have in mind. So our perspectives on what programming and computational tools we use are fairly different. And communication is essential, right? For us, explaining what we do, communicating our results, if we're academics producing publications and results that others can reproduce and replicate, is a central part of the question. And in all of this space, IPython, I hope, is a project that can play a role. I like to motivate why IPython exists, partly based on a very famous quote that I'm sure many of you have seen, but I still like it a lot. I first saw it on the door of one of my physics professors when I started grad school, and it's this famous quote by Hamming that I think remains relevant. It's from 1962, but I think it's actually all the more relevant today because we can produce a lot more numbers and a lot faster, which means that our ability to produce garbage has only increased exponentially if we don't understand what questions we're asking. And so the context that I have in mind is is this kind of very schematic life cycle of the kind of work that we do. We do individual exploratory work with code, with data, with algorithms. We at some point need to collaborate with others typically, whether it's in-house or at other institutions. Often we need to move our code into production environments. We will publish it in some fashion, the results of that work, hopefully. And by publication, I may mean writing an academic paper or writing a book, but it may mean writing a blog post. It may mean writing a report to a business unit inside the company if you're in industry. It's basically, the point is communication, not publication in the sense necessarily of a paper. And for many of us, education, this is a form of education. What we are all doing here presenting talks is a form of education. And if you're in academia, this tends to be a hamster wheel where you repeat with a slice for writing a grant in the middle there at some point, typically. And so the question is, can we build tools that make this entire process a more fluid one, a smoother one, where the transitions between these stages are not jarring and sharp and broken by having emailed a zip file with a bunch of funnily named files to a colleague and having to rewrite your MATLAB prototype in C++ so you can run it in production and copy-pasting the figures into a Word manuscript. Can we build tools where all of this is much more smoothly integrated? And I would argue that the answer is yes, and that with IPython we are tackling this problem in kind of an integrated way. IPython was born out of just the needs of somebody, in my case, in particle physics and in applied mathematics and analyzing brain imaging data, just doing kind of probably very similar things to the things you guys do. In my case, using the scientific Python stack, NumPy, SciPy, Matplotlib, etc., wanting to effectively run code, iterate on it, plot my data, view my results, and do so in a very fluid manner. And it was born as basically as an enhanced Python interactive shell. As computer science call them, a REPL. REPL stands for read, eval, print, loop, and it's a common term in computer science lingo. It's the interactive environment where you type your code and you see your results. And IPython started as a better interactive REPL for Python, but over time it has evolved into a fairly abstract collection of tools that actually does lots of things. Eventually it became this graphical terminal, kind of a shell for scientists, where you could not only type code and run it, but actually see the results right there, even if they included plots. So it felt like a terminal, but it was actually a terminal with graphical capabilities and syntax highlighting and things of that nature. And in order to build this, we abstracted the idea of what a REPL is into a network protocol. And so instead of simply reading code and executing it and printing the answer, which is what REPL does, reads, evaluates, prints, and does a loop, we took those ideas, abstracted them into a protocol where a process could listen to input, execute it, and return the answers so that another client, in this case this graphical terminal, could display it. And that led to the system, our real ultimate goal was to build an environment where we could combine not only code and results, but also communication. And this is what we call the IPython notebook. Those of you who have used systems like Maple or Mathematica are probably familiar with notebook-like systems. I was a heavy user of both of them in my physics and mathematics days. And so the IPython notebooks take similar ideas and tries to bring them to the 21st century, to the context of the web and the notion of language-agnostic protocols. And so we have built a system that runs in the web browser and where you can combine code execution, results, narrative, collaboration, all of it in a web browser. So this talk is actually an IPython notebook. This is running inside of Chrome. And is actually a presentation. But I can actually run code. So for example, I can type a couple of lines of Python code, in this case using pandas to grab some stock data and plot it. And I have 3 lines of code that execute something and return a nicely formatted HTML table for a data set and a plot in this case of the open and adjusted close statistics for the IBM stock price since 2012, for example. But in addition to that, I can display any other kinds of data. So what we've done with IPython is begin to think, well, the moment we start running code in a web browser, we should embrace the fact that web browsers are rich platforms that can represent many kinds of data, and we can allow our computations to return different kinds of output. So in this case, let's imagine I have a time series that actually is an audio signal. I can plot the data either in the time domain or in the spectral domain, or I can return an audio object that is actually an embedded HTML5.
How much wood would a woodchuck chuck if a woodchuck could chuck wood?
Is an embedded audio object. So these are 3 ways of looking at the same data set, which is actually a computation. I asked for something and code ran and returned an object, but that object is something that a web browser is capable of displaying with what web browsers can do today. So it's this idea of executing code and embracing sort of the modern protocols and data types of the web, including things like, well, mathematics. We are, after all, scientists, and so and browsers have gone a long ways, fortunately, in terms of their ability to actually display mathematics. So what IPython lets me do is include text and LaTeX that is nicely rendered. When I render it, the LaTeX is nicely rendered by a library called MathJax into math. But I can also execute that code and return values that are also themselves rendered symbolically, so that I can include not only narrative mathematics, but actually results that are rendered mathematically. In this case, I'm using SymPy, which is a symbolic computing library in Python. So we've tried to build a tool that really sort of gives us all of the pieces for the kinds of data and technical narratives that we build, but that include computation at their heart. And in addition to interacting in the sense of typing code, we've built machinery, and as we'll see later, this is language independent, but for now I'm showing examples of it in Python. We've built machinery to interact with our results not only by typing code. This is the expansion of a simple equation that I showed with SymPy that I showed in the previous slide. But let's imagine that I want to show what happens as I vary this exponent, which in this case is 2. If I want to interact with that, obviously one option is to go back in here and change this to 4 and run the code again. But I can also simply put this block of code in a little function and say that I want to interact with it with n varying from 1 to 10. And then as I vary that parameter, have the code be automatically evaluated, recomputed, and the result returned. So the idea is, can we build back to this question of, as scientists, we want to have interactive control that couples our code, our algorithms, our data, and our results in a very tight way. Can we build tools that allow us to explore our questions, but with the amount of software engineering that we as scientists are willing to put in, which is, at least I'm not going to write GUI code. Okay, I'm old enough that I'm going to die without actually writing custom GUI code. GUIs are complicated things to write and debug and develop. They're expensive in the sense of development time to build. But they can be useful because there are problems where having graphical controls is useful. So the question is, can we build tools that allow us to explore code only by writing a minimal amount of code that we as scientists are willing to write, and that yet give us enough graphical control over things like parameters and whatnot to understand what's happening with our code and data without necessarily getting into the business of writing a full-blown graphical interface, like you would say, to write a program like, say, Photoshop or Microsoft Word or Excel or whatever. So this is what we've tried to capture. Basically, what are the patterns of interacting with code with graphical controls that are useful for working scientists and that give us the kind of control that we need. And hopefully, this is something where, with another simple example, we can see the value of, let's say that we have an image, and we're teaching a course on basic image processing, and we want to illustrate what happens if we convolve that image with a Gaussian filter, or rescale any of its red, green, or blue channels by a parameter. So this would be the kind of thing where you can write a very simple 3-4 line function to show your students what is the channel structure of a standard RGB image. But obviously, rather than running this 100 times, it would be nice if you could say, well, now let me interact with that. Let me interact with that function by working on my fixed image, but varying the width of the Gaussian kernel between 0 and 10, and varying the red, green, and blue channels in this range. And as I slide this, I see that the code gets called again and gets evaluated, and I see the result. And as I vary, say, my red, green, and blue saturation parameters, I can see what happens to the image. The point is, this is very simple parameter exploration. In this case, I'm running a simple local code. You could be calling back to your cluster and tweaking parameters in your classifier and seeing the results immediately. And this is the only code that you had to write to get that GUI. That's it. It's one line of code that is saying, I want to interact with my code over the following parameter range, and the rest happens automatically. And so these tools have been built in a language-agnostic way, because in IPython, what we've done is abstract this notion of executing code and getting results back as a generic protocol that works with many programming languages. So in this case, I do most of my work in Python, but let's say that you need to call R for something because it happens to have a library that you need. We make it very easy for you to say, you have a data set in Python that you want to start with, but you need R support. You can say here, the following block of code is R. By typing $R, it signals that the next block of code is R and not Python, that X and Y are inputs, and that when the code is finished executing, you need XY coef as an output. And then this is R syntax, which executes, and those of you who recognize R will see that this is the standard summary for a linear fit, and those are the standard summary plots for a linear model in R. And when you get back your answer, you have a variable that you can continue using in Python. So you can mix as you go languages in order to achieve the scientific result that you're interested in, which is not necessarily developing software in Python, but actually answering a question for which you may need a library in another language. Some of you may be interested in Julia, which is a recent effort in numerical computing out of MIT with a lot of really interesting ideas. So the same idea, once you load the Julia support, you can say, well, this block of code is written in Julia, and in fact, interestingly here, there's a little bit of a mind bender in that in Julia, we're calling back Python libraries. So in fact, we're initializing a Julia runtime, but the Julia runtime is linked back in memory to the Python runtime that called it, so it's kind of a snake biting its own head. And so we create a data set that has been computed by calling the sine function from Julia and the numpy function, the numpy cosine function, and then is being plotted with the Python matplotlib library back to Python. And then I can grab the actual data, which was S. I could grab it as a Julia variable back into Python and then simply plot it in Python. So the idea is, yes, question?
Just in this example, how much data interchange is going on between all the different languages?
Very, very little. Julia actually has, is building its arrays as pointers to the same underlying NumPy arrays. And you can see that basically by grabbing a variable on both languages and modifying pieces of it and seeing that you're actually operating in place. So there's as little data copying as possible. There is some, but actually quite very little. The question was for the recording, how much data copying is going on? I'm sorry, I should have repeated that initially. Fortran, still a workhorse, but we still need it for a lot of things. And you might like to use Fortran as an interactive tool. So in this case, I've written a Fortran subroutine, and I can call it as a normal Python function afterwards and use it. And this allows me to do, maybe I wanted sine of x squared instead. And so I can use Fortran as a scripting language effectively by including subroutines that get compiled and linked at runtime into the same process that had already loaded Julia and R and the Python library. So this is all running in one process. And all of these tools, so this is the computational part, but as I said, it's important for us, what we want to build is a platform for not only for computation, but also for collaboration. And so we've built a service that allows you to share your work with others in as painless a way as possible. The files that I'm using are IPython notebooks. These are actually files on disk. And we have a service called the IPython NB Viewer that runs at nbviewer.ipython.org, which will let you render a notebook as a web page for others to see by simply providing a URL. And this service is being widely used by many to share content on many topics. So I'm going to show you a couple, simply to illustrate a couple of examples. This is a long analysis of a study of weather data and crime statistics in the city of Chicago by a social scientist in Chicago who created this very long and detailed analysis. But the point is here, I am actually displaying a web page. This is not, I'm not running code here, I'm looking at a web page. So he can share this work with the world without having anyone install anything. Just by providing that URL, it will be rendered as a normal web page and I can view it. There's no code that I can run here. It looks the same, but I can't actually run anything. This is a static web page. But if I want, I can download that. I click here, and then I've downloaded that notebook. My browser has downloaded it, and now I could execute it locally if I wanted to. So we've tried to reduce the barrier to sharing and collaborating on this kind of work to a minimum. Here's another example of a wave propagation and geophysical sonic well modeling, for example. This is for people who do kind of seismics in geophysics. These are standard plots. And here we have a gallery of notebooks that people are sharing with the system on a huge variety of topics. I'm just going to leave that index there. I'm not going to go into details, but you can see that people are sharing work, anything from single notebooks on specific topics, notebooks that replicate results in academic publications, all the way to entire courses on a variety of topics, from quantum optics to scientific computing. And then this idea of communication, as I said, should go these days not only to technical papers and the academic literature, but also to things like blogs and kind of more informal web-based communication. And it has become very easy to do so with this platform. So this is an example of a blog post by Jake Vanderplas at the University of Washington in Seattle, who recently wrote about whether the uptick that apparently the city of Seattle is seeing in cycling is related to weather changes. And it's this really interesting analysis of data from the city of Seattle. But this is his blog. This is just the website of his blog. But the blog post is actually a notebook, which you can download and run yourself and question the assumptions behind his analysis and so on and so forth. So if you go to the bottom, there is a discussion from other people, as is standard on any blog, talking about the value of the analysis and his assumptions and so on and so forth. But the point is, In this case, anyone who's interested in having that conversation with him, if they have any question about his assumptions, all they have to do is grab that blog post and simply click, download it, grab the data, and re-execute it themselves. So we think we're beginning to have a tool that by integrating the whole pipeline from one end to the other makes the discussion a little bit more informed than it was before. Entire books are being written with these tools. So this is an example of a standard hardcover Springer academic book on signal processing, kind of a statistical bent on signal processing, where the whole book was actually written as a collection of these notebooks, which you can download from a GitHub repository. So you can go to GitHub and actually download the book and execute every chapter in the book. So there's no question about whether the scripts in the book that you see are the ones that generated the figures, whether the author copied and pasted right, whether they have make files that did everything in the right order, because simply every chapter was actually executed, and when you read the book, you can go and grab and execute it yourself. And furthermore, he actually posted each chapter as he was writing it as a blog post, as a blog entry. So this was kind of unifying the whole workflow from notebooks to ongoing public blog discussion to publicly accessible posts on GitHub to a finished hardcover $90 on Amazon kind of book published by Springer. And all of this is based on a fairly simple and generic architecture where, going back to where I started, there's a piece of code in the middle that is this kernel that executes whatever is asked of it and returns results, and to which now that we have a protocol, other clients can connect, either a terminal, we still have a terminal standard old-fashioned client that continues to exist. That graphical console that I showed before is actually written in the Qt GUI toolkit and is still there, or the web notebook that we have, and all of these clients speak that protocol and can communicate with this kernel process that speaks the protocol. So you can think of this as HTTP and HTML, which were designed for sharing code, for sharing content or between servers and clients, between web servers and web browsers. You can think of this as the equivalent of HTTP and HTML, but for sharing computation, right? Where instead of rendering content, you're executing code and you're returning computational results. So we effectively have a protocol for computation and we have a format for recording computation. These same tools, I don't have time to go into this, but these same tools enable high-level interactive parallel computing over the same protocols and abstractions, but that's kind of a long topic for a separate talk. And the point is that the moment you abstract these things in this fashion, then it becomes possible to really say, let's do this with other tools and other languages. So these protocols have been implemented by now in a variety of languages. And so there's actually independent implementations of these protocols in multiple languages. I am briefly going to show you only the Julia one and the R one, because I think they're the most interesting to this audience. This is an example of a notebook that is now running in Julia. So the syntax here is pure Julia syntax. There's no Python anywhere. This is running in pure Julia, and if I execute this code, this is a cute example of various ways of generating fractals, but the point is this is Julia code. This is not Python code at all, and yet the format, the document, the collaboration infrastructure is 100% the same, because at the end of the day what matters is algorithmic work, scientific questions, the sharing of our work and results. It's not really the programming language is not what matters. And similarly, we have a kernel for R. So this is an example of running. This is, for those of you who know R, you'll recognize that this is our syntax, and this is using the leaflet library, which is one of these kind of real-time interactive JavaScript libraries for mapping. I'm probably not connected to the web, which is probably why it's not re-rendering right, because I forgot to reconnect to the internet. But this is a JavaScript library that does routing, and right now it's failing to recompute the route because I didn't connect to the web, and I'm not going to bother in the interest of time. But the point is, in this case, the code that is executed is pure R. So if you're not interested in Python, it doesn't matter. The name IPython basically is a historically interesting name, but today what we've really built is a protocol for scientific computation across languages. And so this has led to a fairly healthy ecosystem of not only these languages, but actually entire frameworks and platforms, both open source and commercial. One particularly interesting one that we're very happy about is a product out of Google Research called Collaboratory. I mentioned it recently in Taiwan. This has not been released yet. We will make an actual release of this product in about 2 weeks. It was built at the New York City Google Research offices. analysis. And what it provides is IPython in Google Docs. And so let's see if I can connect to the web I guess I should connect to the web so that this actually works. So if I am in Google Docs and I have Collaboratory installed, this is my Google Docs. When I ask to create, in addition to document, etc., I can create a notebook. And here's an example of one that I had pre-opened, where I have a notebook created on Google Docs, and as you can see, this is my standard kind of, any of you who has done Google Doc sharing and whatnot is used to seeing the faces of your collaborators. If one of you was logged in here, your face would appear there. You can see that this is a line that I ran. This is a line that Wes McKinney ran when we ran this demo together a few weeks ago. He ran that cell from the audience, and so it recorded that he ran it. And if I run this one here, it will produce these results. I can change the code, and it's kind of standard. I can change the number of points that are plotted. This is standard NumPy and Matplotlib code. This is running entirely in my browser, where the entire system was deployed as a Google Chrome app that runs fully in the browser. So it's kind of a zero deploy option. And the documents are automatically stored in the Google Docs environment, in the Google Drive, I guess they call it these days, environment. So this is going to actually be released as an open source repository in a couple of weeks. We're kind of finishing the cleanup of the repo, and this will be part of the IPython project as an open source product for anyone to add. It's still very, very much, I wouldn't even call it beta, I would still call it kind of alpha. There's still a lot of rough edges, but we're very excited about the possibilities that this opens up. Google is not the only one. The IBM Watson team built machinery using IPython to train Watson. They have a talk online. In the interest of time, I'm going to kind of quickly skip over this. Enthought, a company in Austin that develops a scientific IDE that bundles Python, but so does Microsoft. Visual Studio actually now has a plugin for Python that includes IPython that lets you actually do sort of scientific computing and data-intensive things inside of Visual Studio using the same things. And this is a completely independent implementation that shows how once you have these protocols, third parties can build these things into their own products independent of us. Star Cluster, which Xavier mentioned in his talk yesterday, is an open source project out of MIT to easily deploy AWS clusters that can ship as an IPython parallel cluster with a notebook server. There are companies that offer notebooks online. Continuum Analytics is one out of Austin that has a system called Wakari. There's another one out of the University of Washington called SageMath Cloud that also offers hosted notebooks online. And GraphLab, which I'm sure many in this crowd know, also has an IPython-based GraphLab notebook that at least I saw on their website. This was a screenshot from their website recently. And I'm going to wrap up by simply mentioning that obviously this isn't work that I've done. This may have started as my personal PhD procrastination project, hiding away from my advisor. But these days, all of the hard work is really done by a very talented team. In particular, I want to highlight Brian Granger, who's a physics professor down the road in San Luis Obispo in Cal Poly, who's my co-PI in several of the grants that fund the project. And we have support from both industry and academic funding. So this is an interesting project where sort of the open source nature of the project leads to an interesting collaboration between traditional federal agencies, private funders, and also industry. In particular, Microsoft Research and Rackspace have been really generous with us. So just to wrap up, so we have a minute or two for questions, hopefully I've shown you that there is some value in building language-agnostic protocols and tools that really take a step back over the everyday workflows that we tend to have in scientific computing and data analysis, and that enable and support collaboration, reproducibility, sharing across languages, across tools, across themes, kind of embracing the web in a better way, and in particular that give us kind of a small set of tools to tackle this very broad set of challenges, and that allow us, because precisely of the architecture, to put the computation wherever the data and the resources are. Because in this case, since the only thing you need is a web browser, there's actually an iPad app that ships all of this that's coming out, I think, in a few weeks, that actually lets you run all of this in an iPad. So the moment you kind of design things in this manner, then it becomes a lot easier to sort of decouple where are the computational resources and where is the actual, sort of where is your brain and where are your eyes and your hands. Thank you very much. I think I have maybe 1 or 2 minutes for a question, but I know we're tight. Thank you. No, so the question is whether R and all these other languages supported in the Chrome build. Yes and no. There's two ways in which the Chrome one can run. The Chrome one can actually, what I said there is that it runs purely inside of Chrome as a bundle in the browser. It can also run against a normal local kernel, basically in a hybrid way where the document storage is Google Docs, but the code execution is the normal kernel. In that mode, it can in principle run against the normal one. In the fully in the browser mode, right now it can't, but there's no reason why it can't. It's just that the first prototype only compiled NumPy and Matplotlib. That was it. We had to start somewhere. But there's no technical reason why it can't, why you couldn't produce a bundle that includes R or Julia or any of the other tools. So right now, the most immediate, the question was after the Google Docs, what other features are we working on? Right now, the two key things that we're working on are allowing you to share statically, without a kernel executing code, interactive JavaScript controls where you don't have a kernel that can execute the code. Right now, whenever you drag a control, there has to be something in the back executing code. And so we're building a design where you can effectively record and pre-compute those values and cache them so that you could imagine sharing supplementary materials about a paper that actually include parameter exploration. And so that you could share in the supplementary materials section of the paper, you could actually share a notebook where the audience can play back parameters, maybe not over ranges you hadn't included, but at least you can expose not just the static image, but actual parameter exploration. That's one thing. And the second one is a proper multi-user notebook server so that more than one user can log in and so that you can run a notebook server, say for a research group or a class or a university. Not something at internet sort of company scale, but sort of small and medium-sized group scale. So we're working on both of those things. Probably the last question. I'd be happy to take questions afterwards. I don't want to delay the. So the question is, are there any educational platforms? I do know, for example, that there is, and in that gallery, there's links to high school computer science teaching materials. And I do know that there are a number of educators in computer science who are beginning to write materials with this, and a lot of undergraduate physics courses that are beginning to write lab materials with this. But obviously, we don't centralize any of that, so often it's a matter of seeing somebody make a post about it. If you spot something, I encourage you to put it on that gallery so that at least it's a little bit easier to find. But we're certainly seeing a lot of interest and people writing a lot of educational materials. The bulk of it so far has been at the university level, but it's beginning to happen at kind of for younger audiences. Let's do it later. Thank you very much.